Welcome to this BBB Industry segment on electrical fundamentals.
Yeah, electricity all over cars today. So let's get started. In our experience, professional installers often lose perspective how automotive electrical systems work, and more importantly, figuring out problems when they're not working.
And this will help you build a firm foundation and see how electricity works behind the scenes.
Yeah, we'll stick to the basics here. We'll start out with atoms and electron flow, outer electrons in the orbit ring. We'll go over to circuit designs, like a series circuit here, a parallel circuit, a series parallel circuit. We'll throw in a little bit of magnetism, conductors, insulators. We'll talk about Ohm's law and how it applies to electricals, and we'll wind this thing up with some circuit faults.
And this will help you build a firm foundation so you can tackle any electrical problem.
It doesn't matter whether you're working on a car in a shop as a master technician, or just an entry-level technician, or even in your backyard. You have to know base electrical to fix the car right the first time. Base electrical is key. Let's start out with defining electricity. Now, electricity is a general term dealing with electron movement, either present or static, sitting still. Doesn't make a difference. Electricity all starts with matter. Matter is, this table has matter, you have matter, and then there's those little atoms. Think back to science class. You remember in science class we had the protons, the neutrons, and the electrons? Well, this solar system gives us a good display of that. Inside of here are our protons and our neutrons, and in the outer orbit ring floating around inside of there is that electron. That electron is what we're concerned with because we want to deal with that electron for electricity movement. Now, we need to understand two terms with that electron, conductors and insulators. Now, I have a piece of wire here. This wire is a conductor on the inside. The inside here is copper, and that has 4 electrons in that outer orbit ring or less. The insulator, though, is made of rubber. Now, this insulator on the outside, that's 8 electrons or more. That's going to oppose the current flow and keep it running through that wire. Now, you got a good demonstration to show that. Why don't you show me your spark tester?
All right, over here on this spark tester, we have electrical wires coming up and over to the spark plug. And these wires are made of rubber, so that's a very good insulator. And then we have our spark plug, which is a very good conductor. And I'll go ahead and turn it on. And if I was to touch that, it's going to shock me. So that makes it a really good conductor.
Let's talk about electricity movement, current, inductance, those outer electrons moving in that outer orbit ring. What we have here is our solar demonstration. Now we have that outer electron, and what's going to happen is he's going to go around on the outside of that. That's the guy we're concerned with, that outer electron. Now, to make a crude illustration, as he's going around here, I can actually flick him off, and as he flick him off, he's going to jump on to the next one, knock him off, and down the line he goes. But we have to understand the concepts of insulators and conductors. If we had 4 or more of those guys, actually 8 or more, 4 to 8 make a good semiconductor, he's in the middle. But 8 or more of those outer electrons, that's a good insulator. Now, if I took Chase and I took 8 of Chases and I put them in a big group and I tried to hit him, he's not going anywhere. That's a good insulator. But if I took 4 or less of Chases and I hit him, he'll fly off and he'll hit the other one. And down the line they go. But we have to understand a little bit about magnetism and what pushes them. We got this magnet illustration here, and if I take 2 unlike charges and I put them together, they're going to attract. If Chase takes the like charges and tries to put them together, they're going to repel each other. Now, that's the concept of a battery. A battery is a pressure maker, electromotive force. We have a potential difference from the positive to the negative terminal. That positive-negative difference is going to attract the negative electrons to get them to move. A battery is an electrochemical pressure maker. An alternator is a mechanical pressure maker.
And over here on the starter board, let me show you how this works. We're going to run our power up to our switch, maybe a relay, and we're going to come over to the starter to do some kind of work. When you hit the key, there's your work. And then it's going to return to the negative side of that battery.
And that's important. 2 kinds of current flow we can also discuss here. We have electron flow. Well, scientists, they like to use electron flow. They say that the electrons go from the negative to the positive side of the battery. Car guys, we like to use conventional flow, from the positive to the negative. Remember, schematics are written in conventional theory. They start from the positive and go to the negative. Now I know this is all hard to visualize, this electron movement, and I'll tell you why. Because those electrons are going 6.28 billion of them are running through that wire every second in 1 amp of electricity.
And we're going to need a meter to count all that. And we need to talk about a couple of terms: voltage, current, and resistance.
In order to understand those 3 terms, voltage, current, and resistance, we can use a water demonstration, because you have to understand water behaves a lot like electricity. Now if Chase takes this jug and he fills up this vat right here, this is voltage. He's filling up the jug with pressure, water pressure, electromotive force. The higher it gets, the more pressure's building. Now a battery, electrochemical pressure, an alternator, mechanical pressure, but pressure nevertheless. That pressure builds. In a minute, we're going to pull the plug. When we pull the plug, the water is going to flow out of there and through it. As it flows through it, that's current. Inductance, that's actually movement of our electron flows, the same thing. And then we're going to use that water wheel for resistance, opposition to current flow. That's what resistance is, opposition to current flow. He's going to slow down the current flow a little bit, and it's going to spin that wheel in the form of work. So go ahead and pull that plug. And what you see is the water's draining. As it drains down, the pressure's getting depleted out of the battery, the current flow starts to stop, and the work stops happening. That's a good look at voltage, current, and resistance. Now we use a meter to measure those. We measure volts in voltage. We measure amps in amperage, that's current flow, and we measure resistance in ohms. Now, there's a relationship called Ohm's law. We can take a look at that in some circuits and understand how this all works. All right, Ohm's law states that current in a circuit is proportional to the voltage or the pressure, potential difference. And then we throw in that variable of resistance. Now there's a whole mathematical chart here that shows Ohm's law and how it works.
It's important that you have voltage, current, and amperage in a system to work correctly.
Yeah, and we're going to look at that. It's easier just to look at it on the board. We'll start out here with a series circuit. We have 3 circuits on this board. Chase will demonstrate this series circuit.
Okay, what we got is our wiring. We got a circuit protection, a switch, and we got 2 light bulbs in here. Now think of your inexpensive Christmas lights. If you pull out one, all the power goes dead on that whole line.
That's because they're in series. Both of these bulbs are in line. Now this circuit over here, this one here is a parallel circuit, a little bit different. Ohm's law states in his circuit that we're going to drop all the voltage and the voltage is going to be used up. And we'll demonstrate that in a minute with our meter. But let's look at this parallel circuit. Now our parallel circuit, Ohm's law says that we're going to drop 12 volts down each one of these branches. I don't care if you have 1 branch or 800 branches. 12 volts is going to get divided down each one of them. Now as it goes down those branches, it's going to light those bulbs. If I pull one bulb out, the other one's still going to burn because it's on its own circuit. Think of that expensive set of Christmas lights. A little bit better. If you purchase them, you're in good shape. Now, the last circuit we're going to look at, that's a series parallel. And why it's a series parallel circuit is because we threw a resistor in the mix. He's in series with the parallel. Now, the parallel, the Ohm's law is going to still be the same. We got our voltage down here, and our amperage down this circuit is going to be determined by the resistance value of the bulbs. All right? Now, I can take this resistance and I can vary it. I can turn it up, or I can bring some resistance. Let this switch do resistance. Remember, that's opposition to current flow. He's using up some of the electricity, and these guys are burning dim. Now, we can take our meter, and we can actually prove Ohm's law. Ohm's law states that the voltage drops have to equal the source voltage. So Chase has his meter set up on volts. He's going across the battery terminals. And our meter's showing 12.95 approximately. Then he comes over to the first light bulb. When he goes across the first light bulb, that's measuring voltage drop. What happened is we have 6.35 drop there. So if he goes across his next bulb, we're hoping he has 6.35. or close to it. So all that voltage was used up before it went back home to the battery. If it didn't, that would be a direct short. Now these are good properly operating circuits, but we can take them, short them, have some fun, and look at what bad circuits do.
Now to the fun stuff. Let's go ahead and create a short circuit.
Yeah, there's 3 types of short circuits we need to look at. The first one's an open, and then we'll look at some shorts. But an open's easy. Demonstrate an open for them.
Over here on this board, I'm going to open this switch here, and what that does is create an open. Or you can simply pull a bulb, that's an open. Or a cut wire's an open.
Anything that electron flow stops, that's the end of that. That's an open circuit. Now the other two, a little more difficult. We have a short. We can have a short to power, or we can have a short to ground. When I think about a short to power, I like to think about copper to copper, copper touching copper. And if you take that wire and you reach and you short that bulb out over here, what happens? Electricity is lazy. It's going to take the path of least resistance. So what it does is it all runs through that bulb and the other bulb went out. Now they're hard to detect. That's where your components may work or not work. Depending on the fuse in the circuit, will depend if the fuse blows or not. It's just how many amps it's going to draw. Now our other one, a little easier to detect. That's a short to ground. We're talking about copper to steel. Now if you come over, we have protection devices. 3 types of protection devices. We start out here with a fuse, then we're going to move on to a circuit breaker, and then from the circuit breaker we're going to show you a fusible link. We'll start out with the fuse. The fuse is a one-time protection device. It's rated by amps, the amps. Anytime we go short to ground, you're going to run the amps so fast through that circuit, it's going to create heat. When it creates heat, there's no opposition to current flow, it's going to blow that fuse. So if you watch closely, you just take that circuit and purposely short it to ground, and that fuse blows. No lights, that's it. You're done with that circuit. You need to go ahead and find out where the short is and repair it. Now, our next one's a circuit breaker. He's a resettable device, if you will. He will open. What he is he's actually a bimetallic piece here. This bimetallic piece is going to heat up. It's going to open. Once it cools down, it closes the circuit again. Think about mechanical resistance, something that's causing a lot of amps to flow. That's going to do that. So if you come over and you short him to ground, what's going to happen here is he's actually going to cut the lights out. Now if you wait a minute, what's going to happen is cools down and the lights come back on. Now our last protection device, that's a fusible link. That's a one-time protection device too. That's going to burn. That's 4 AUG American wire gauges smaller than the wire it's protecting. Okay, so remember, the bigger the number, the smaller the wire. So if we're dealing with a 16 gauge wire, you're dealing with a 20 gauge fusible link. That's usually up under the hood, somewhere before we get to the fuse block. Starters, alternators, a lot of times are protected by fusible links. And we'll burn that in a minute because that's a lot of fun. Now remember, all these circuit faults, all this base electrical is critical to understand and fix cars. This Volt over here, he's full of electric. Matter of fact, he runs off electric. So if you understand the basis of electricity, you can fix anything. Chase, why don't you show us a little bit of fun and burn this fusible link. Go ahead and hook up your battery, then take your jumper wire, simply go across the hot terminal directly to ground, and there it goes. You took a good look at basic electrical, all the way from the atoms to circuit intent. Everything you need to know to fix a car professionally. You need to know about circuit design, circuit intent, breakers, wires, everything we looked at. We burnt some fusible links. We had a good time.
Yeah, and for more information on any vehicle-related problems, you can log on to bbbind.com.
Yeah, you'll find troubleshooting hints, you'll find troubleshooting videos, wire diagrams, TSBs for the entire vehicle, and so much more. Thanks for watching.